Something is off with reality, and a machine just confirmed it. A quantum chip, smaller than a coin, has now run experiments that strip away one of the deepest beliefs we hold: that the world is sitting there with definite properties, whether anyone looks or not. It isn't. Not in the way you think. Real labs, real hardware, real measurements. Photon experiments earned a Nobel Prize in 2022 for the same verdict, and superconducting qubits have since repeated it without the old loopholes. You are about to walk through how a calculation became a courtroom, why two honest observers can disagree about what just happened, why the past behaves like it is still being decided, and what physicists must give up to keep their equations consistent. If you find this strange, useful, or worth defending, hit subscribe. It keeps these investigations alive. Now hold steady. The deeper answer is worse than the headline. A small refrigerator in a quiet lab is humming at a temperature colder than deep space. Inside it sits a chip the size of a fingernail. That chip is doing something Isaac Newton would have called impossible. It is testing whether the world exists the way we think it does when nobody's looking. For most of human history, this question lived in philosophy. You looked at a tree. You assumed the tree was there before you looked. You assumed the tree would still be there after you walked away. That assumption felt so basic, it never needed a name. Physics had a name for it anyway. Local realism. Two ideas stitched together. First, that things have properties whether you check them or not. Second, that nothing can reach across empty space faster than light to influence something far away. Newton believed it. Einstein believed it harder than almost anyone in history. Most working scientists treated it as the floor of physics, the part you stand on while you do everything else. Then quantum mechanics came along and started cracking the floor. For decades, the cracks lived only in equations. Physicists could write down strange predictions, but no experiment had ever forced reality to choose. The two pictures of the world simply argued at each other on paper. That argument is now over. Quantum computers, the same machines being built by Google, IBM, and a small army of startups, have become something nobody quite advertised. They have become laboratories for testing the basement of reality itself. The experiments inside them are not predictions. They are measurements. And the measurements keep delivering the same answer. Local realism does not survive contact with the real world. That single sentence is doing more work than it sounds like. It means at least one of the assumptions you wake up with every morning is broken. Either things do not have definite properties before you check them, or something is signaling across space faster than light. Or you do not really get to choose what you measure. Pick one. Physics no longer lets you keep all three. The reason this matters now, and not 50 years ago, is hardware. The early experiments were brilliant but fragile. They could be argued with. Every result had a loophole somebody could squeeze through to keep the old picture alive. One by one, those loopholes have closed. Photon experiments closed them in 2015. Superconducting circuits, the same chips inside today's quantum computers, closed them again with a different technology a few years later. The verdict has come back from multiple platforms, in multiple countries, using completely different physics. Same answer every time. The Nobel Prize in Physics in 2022 went to 3 scientists for exactly this work. The committee did not call it horrifying. Committees rarely use that word. But read between the lines and the meaning is plain. The world they confirmed is not the world Newton described. It is not the world your eyes describe either. To understand why this is so unsettling, we have to go back to what reality used to mean before quantum mechanics put a chisel to it. Because the assumption that broke was not some technical detail. It was the floor. Pick up a coffee cup. You believe it is there. You believe it has a weight, a position, a temperature, all of them sitting at definite values whether you measure them or not. Walk out of the room, the cup stays. Come back in an hour. The cup is right where you left it. That whole picture has a name in physics. Realism. The idea that physical things carry their own properties, locked in, independent of you. For 300 years, it was not even controversial. It was the silent agreement underneath every equation. Newton wrote his laws inside this picture. Maxwell wrote his electromagnetism inside it. The whole machinery of classical physics assumes that the universe is a giant, definite, ticking object that you happen to be standing inside. Then a second assumption joined it: locality. The idea that nothing in this giant ticking object can poke something far away without sending a signal. The signal has to travel. The signal has a speed limit. Einstein nailed that limit down with relativity. Light and nothing faster. Stitch the two together and you get local realism. Things have properties. Influences travel through space at finite speed. End of story. Most of the everyday world runs on this picture and it works beautifully. Bridges hold up, planes fly, phones connect. Every engineer alive uses local realism without thinking about it. Then, the small things misbehaved. In the early 20th century, physicists peering at atoms started getting answers that did not fit. Electrons did not seem to have a position until you looked. Light acted like a wave when you set up one experiment and like a particle when you set up another. Particles separated by a wide gap behaved as if they were holding hands across it. The math that described all this, quantum mechanics, predicted everything correctly. But it described a world that did not feel real in the old sense. You could not say where the electron was. You could only say where it would probably be when you measured it. Before measurement, the electron lived in something called a superposition, a blurry overlap of possibilities. Only the act of looking forced it to pick one. This bothered people. It bothered Einstein the most. He could not accept that the universe was that loose. To him, the equations had to be hiding something. There must be deeper variables, properties that the electron carried all along, that quantum theory simply did not see yet. The blur was not real. The blur was ignorance. Once we found the missing pieces, the world would look solid again. This is the bet he made. He made it loudly in print in 1935, in a paper now known by 3 letters: E.P.R. Einstein, Podolsky, Rosen. Their argument was a trap. They constructed a thought experiment where, if quantum theory were complete, 2 distant particles would have to talk to each other instantly. That, they argued, was absurd. Therefore, quantum theory was incomplete. Therefore, something deeper had to exist underneath. It was a brilliant attack. It was also wrong. But nobody could prove it was wrong for almost 30 years, because nobody knew how to ask the universe the question directly. Then a quiet Irish physicist named John Bell figured it out. And the only way to understand what Bell did is to understand exactly what Einstein was hiding behind. Einstein needed the world to be solid, not solid in the everyday sense, solid in the deeper sense. He needed the universe to keep existing the same way, whether anyone was watching or not. His argument with quantum mechanics was never really about math. He could do the math. The math worked. His argument was about what the math meant. He believed that any theory that left the world fuzzy until you measured it had to be incomplete. There had to be something underneath, ticking quietly, deciding the answers in advance. Physicists gave that something a name. Hidden variables, invisible properties that travel with each particle, set at the moment of birth, telling it what to do when somebody finally puts a detector in its path. The universe in this picture is still the giant ticking object Newton imagined. It just runs on machinery we have not seen yet. To make this concrete, picture 2 particles created together and flying apart in opposite directions. Quantum mechanics says they share a single linked state called entanglement. Measure one and the other instantly behaves as if it knows what happened, no matter how far away it is. Einstein hated this. He called it spooky action at a distance. He did not believe it could be true. So in 1935, with 2 younger collaborators, he wrote a paper meant to corner quantum theory. The argument went like this: If the two particles really were predicting each other's behavior across a distance, that would violate relativity. Nothing should travel faster than light, including information. Therefore, the particles must have been carrying their answers all along. Hidden variables, case closed. It was a clean trap. Either quantum mechanics broke relativity, or it was incomplete. Einstein bet on incomplete. For 30 years, nobody could test which side was right. The two pictures made the same predictions for almost every experiment you could run. Quantum mechanics with its blur. Hidden variables with their preloaded answers. Both sides shrugged at the data. The argument lived in journals and lecture halls, beautiful and untouchable. What people did not realize is that Einstein's bet had a quiet edge to it. He was not just defending common sense, he was defending three things at once. He was defending the idea that particles have real properties before measurement. He was defending the idea that distant events cannot influence each other instantly. And he was defending the idea that experimenters get to freely choose what to measure. 3 pillars, 3 load-bearing beams under the floor of physics. Take any one of them away and the room you're standing in stops looking the same. Einstein died in 1955, still convinced that quantum mechanics was missing something, still confident that the universe was solid underneath. He never saw the experiment that would put his bet to the test. The man who would build that experiment, on paper first, was working in obscurity at a particle physics center in Switzerland. He was not famous. He was not chasing a Nobel. He was simply bothered. Bothered enough to do something nobody had managed before. He found a way to turn the philosophical fight into a number you could measure. A number that, depending on which way it tilted, would say which picture of reality was correct. His name was John Stuart Bell. And what he wrote in 1964 quietly changed everything that came after. John Bell worked at CERN designing particle accelerators by day. The argument with Einstein was a hobby. A serious one, but still a hobby. In his spare hours, he kept circling the same question. Was there a way to actually test whether hidden variables existed, or was this destined to stay a philosophy seminar forever? In 1964, he published a 4-page paper that almost nobody read at the time. The math inside it was simple enough that an undergraduate could follow it. The consequence was so large it took the field a decade to fully absorb. Bell did something nobody had managed before. He turned Einstein's quiet bet into an inequality, a number with a hard ceiling. The setup was elegant. Take 2 entangled particles, send them in opposite directions. Let 2 distant experimenters each measure their particle along an angle the experimenter chooses freely. Repeat many times. Tally up how often the 2 results agree. Now ask one question. If the universe really did run on hidden variables, with locally real properties carried by each particle, how strongly could those distant results possibly correlate? Bell calculated the maximum. He proved that under the assumptions Einstein wanted to defend, the correlation between the 2 distant measurements could never exceed a specific mathematical limit. Cross that limit and you have proven the universe cannot be both local and real. Stay under it, and Einstein's picture survives. Then Bell calculated what quantum mechanics predicted. Quantum mechanics predicted a number above the limit. That was the gap. That was the entire game. The 2 pictures of reality, which had agreed on every previous experiment, would disagree on this one specific measurement. By a knowable amount, by a testable amount. The argument was no longer philosophical. It had become an experiment waiting to be done. To picture what Bell found, imagine 2 perfectly synchronized dancers in separate rooms. A choreographer in each room shouts out a step at random. The dancers perform. You compare the recordings later and count how often the 2 performances match. If the dancers worked out their routine in advance, locally and realistically, there is a hard ceiling on how often the 2 recordings can match across all the possible step combinations. Bell calculated that ceiling exactly. Quantum mechanics says the dancers will match more often than that. more often than any preloaded routine could possibly produce. As if each dancer is somehow learning, in the instant of performance, what step the other one was just told to do. That extra correlation is the fingerprint of something the classical world cannot explain. The beautiful, terrifying part of Bell's result is that it makes no assumptions about how hidden variables would actually work. It does not need to know what they are or how they're stored. It only needs them to be local and real. Any theory that obeys those two conditions, any theory at all, falls under the same ceiling. So the question stopped being whether Einstein was right in some deep, philosophical way. It became whether nature, when actually asked, would land above the ceiling or below it. Bell himself privately hoped the answer would land below. He had a soft spot for Einstein's worldview. It would take 8 more years before anyone built the apparatus to find out. And when they did, the result would not be a tie. It would not be ambiguous. It would settle the bet, at least for the first round, in the most unwelcome way possible for the people who still wanted reality to behave. The first crack in the floor was about to be cut by a graduate student in Berkeley. In a basement at the University of California, Berkeley in the early 70s, 2 physicists were building something nobody had built before, a machine designed to put Einstein's bet to a real measurement. The senior physicist was John Clauser. His collaborator was a graduate student named Stuart Friedman. The apparatus involved a calcium atom, 2 distant detectors, and a lot of patience. The idea was Bell's, dressed up in hardware. Excite a calcium atom in just the right way and it will release a pair of entangled photons in opposite directions. Each photon's polarization, the direction of its electric field, is correlated with the other. Send each one through a polarizing filter set at a chosen angle. Count how often both photons make it through. Compare angles, tally the correlation, compare the tally to Bell's ceiling. If the number landed below the ceiling, Einstein's hidden variables survived. If it landed above, quantum mechanics had broken the floor. The machine was difficult. The detectors of that era caught only a small fraction of the photons that were actually emitted. The runs took weeks. Clauser, who had read Bell's paper as a student and could not let it go, was personally hoping the result would side with Einstein. He wanted reality to be solid. He thought it would be. The result came in 1972. The number landed above the ceiling. Quantum mechanics had won the round. The 2 distant photons were correlating more strongly than any local hidden variable theory could explain. The universe, at least at the scale of these calcium photons, was not behaving the way Einstein had bet. Clauser was, by his own later admission, disappointed. He had expected to defend the older picture. Instead, his own apparatus had been the first to confirm that the older picture was in serious trouble. The result did not become world news. The wider physics community received it politely and moved on. Many treated it as a curiosity. A few took it seriously. The experimental gap between the 2 pictures had been opened, but it was still narrow, and the apparatus had weaknesses that gave the doubters somewhere to stand. Those weaknesses had a name: loopholes. The detectors were inefficient. Most of the photon pairs went uncounted. To get any number out at all, the team had to assume that the photons they did detect were a fair sample of the ones they did not. That assumption is reasonable and almost certainly true, but it is an assumption. A determined defender of hidden variables could argue that the universe was somehow biasing which photons hit the detector, hiding the rest, and faking the appearance of a quantum result. There was also the locality loophole. The 2 detectors were not far enough apart and the measurement choices were not made fast enough to rule out the possibility that some unknown signal was crossing the apparatus during the experiment. If anything could travel between the 2 ends, even slowly, it could in principle coordinate the results. These were not absurd objections. They were technical gaps, and every gap left in an experiment leaves room for someone to keep believing the older picture. What the Berkeley experiment did was prove the question was answerable. The cracks could be cut. The next 40 years of physics would be a slow, careful war to close every loophole, one by one, until there was no longer anywhere left for Einstein's picture to hide. The cracks would widen with every closure, and the people closing them were about to face an obstacle nobody had expected. The 1972 Berkeley result was the first crack. It was not a clean break. For the next 4 decades, every experiment that confirmed Bell's prediction also left at least one back door open. The defenders of local realism could always point at the back door and say, that is where the deeper truth is hiding. The most stubborn loophole was the detection loophole. Photodetectors in those years were terrible. Most of the photons that arrived were missed. To draw any conclusion from the experiment, scientists had to assume the photons they caught were representative of the ones they did not. This is called fair sampling. It is a small word for a heavy assumption. Without it, the data could not even be analyzed. A clever opponent of quantum mechanics could turn that assumption against you. Imagine, they said, a hidden mechanism that makes some photons easier to detect when they would have shown classical behavior, and harder to detect when they would have shown quantum behavior. The detector is biased without anyone realizing it. The universe in this picture is still local and real. We are just looking at a filtered slice of it. The second main loophole was the locality loophole. To trust a Bell test, you have to be sure that no signal, however slow, could have crossed between the 2 distant measurement stations during the experiment. Otherwise, one detector might be quietly informing the other about its setting, and the apparent correlation is just smuggled coordination dressed up as quantum weirdness. Closing this required real distance. It required random measurement settings chosen so fast that no lightspeed signal could outrun the choice. The early experiments simply did not have that speed or that distance. The gap between detectors was small. The settings changed slowly. A hidden signal could in principle have walked the apparatus. There was a third loophole that took even longer to take seriously. The freedom of choice loophole. The whole logic of Bell's argument assumes that the 2 experimenters truly choose their measurement settings independently of the source. If the choices are not really independent, if some hidden process correlates the settings with the particles in a way nobody notices, then the apparent quantum correlation could again be classical conspiracy. This sounds paranoid, but it is technically possible. And in a question, this fundamental, technically possible matters. For decades, every experiment closed one loophole and left another open. Alain Aspect, in France in the early 80s, made enormous progress on the locality loophole by switching the measurement settings rapidly while the photons were already in flight. His work, refined over many runs, became the gold standard. It was the experiment that finally pushed the larger physics community into accepting that something serious was happening. Aspect's name became attached to the result alongside Bell's, but even Aspect's experiments still leaned on detection efficiency. The photons that escaped the count were a soft place where doubt could live. The defenders of local realism, fewer in number now but still articulate, kept pointing at it. The community knew what was needed. A single experiment that closed the detection loophole, the locality loophole, and the freedom of choice loophole all at once, in the same run, with statistically convincing data. That experiment did not exist. The technology to build it did not exist either. Detectors were not efficient enough. Random number generators were not fast enough. Distances were not long enough. Sources were not bright enough. Every piece would have to mature. It would take until 2015 for all the pieces to arrive in the same building at the same time. When they did, 3 different groups did it almost simultaneously. And one quiet night in the Netherlands, the back door finally closed. In the autumn of 2015, 3 independent teams in 3 different countries did the same thing within a few weeks of each other. They ran Bell experiments with no loopholes left. The first to publish was a group at Delft University in the Netherlands. They used a strange trick. Instead of trying to entangle photons, which always lose efficiency in detection, They entangled the spins of single electrons trapped inside tiny defects in diamond crystals. 2 diamonds, each holding 1 electron, sat on opposite sides of the campus, separated by more than a kilometer. That distance was the whole point. It gave any signal traveling between them too little time to influence the measurement before it was over. The diamonds were each connected to a fast random number generator that picked the measurement angle at the very last possible instant. The electron spins were measured with detectors that caught essentially every event. No fair sampling needed. No detection loophole left. The locality loophole closed by the kilometer of fiber. The freedom of choice loophole closed by the speed of the random generators. All 3 back doors shut at the same time, in the same experiment. The result violated the Bell inequality. Within weeks, 2 more teams reported the same kind of result. One at the National Institute of Standards and Technology in the United States, working with photons and ultra-efficient superconducting detectors. Another at the University of Vienna, led by Anton Zeilinger, also with photons. Different platforms, different approaches, different physical setups. All 3 landed above Bell's ceiling. All 3 closed the loopholes. The verdict was unanimous. Local realism was no longer a viable description of the physical world, not as a serious scientific position. The combined result did not just nudge past the Bell limit, it crossed it by many standard deviations. The kind of statistical confidence that physicists reserve for results they consider settled. The reaction in the field was quiet, but historic. There was no parade. There was a slow, collective acceptance that one of the load-bearing beams under classical physics had been formally cut. Either particles do not have definite properties before measurement, or distant events are linked in ways that ignore the speed of light, or experimenters do not really choose their measurements in the way they think they do. Pick one. The data forces the choice. Most physicists, then and now, give up the realism beam. They accept that quantum systems do not have definite properties until they are measured. The universe at the scale of single particles is genuinely indefinite. The blur Einstein hated is not ignorance. It is the actual structure of the world. A smaller number give up locality. They accept that distant events are linked instantly through entanglement in some way that cannot be used to send information, but is nonetheless real. A very small number, including some serious thinkers, give up free choice and accept superdeterminism. The idea that the apparent randomness of measurement settings was secretly correlated with the particles all along. This is a deeply uncomfortable position because it implies your sense of choosing is part of a larger script. Whichever beam you cut, something that felt obvious about the world is now formally false. In 2022, the Nobel Prize in Physics went to Alan Aspect, John Clauser, and Anton Zeilinger for the long arc of this work. The official citation was technical. The translation is sharper. The committee was acknowledging that the flaw of classical reality had been formally tested, and it had given way. But this is where the story turns. Because closing the loopholes with photons was only the opening act, the next phase would happen inside something stranger. Something that is not a passive experiment at all. A machine that can be told what to measure. Photons are wonderful for Bell tests. They travel fast, they barely interact with anything, and they can be sent down a kilometer of fiber without much loss. But photons are also fragile in their own way. They are single shot. You make them, you measure them, they are gone. You cannot hold one and ask it more than one question. Superconducting qubits are a different animal. They are electrical circuits, etched onto chips, cooled to within a hair of absolute zero. At those temperatures, the metal becomes superconducting. Resistance vanishes, electrons begin to move in lockstep, behaving as a single quantum object. The chip stops being a piece of metal and starts being something that can hold a quantum state, manipulate it, and read it out, all on demand. These are the chips inside a modern quantum computer. In 2023, a team published in Nature a result that closed the loop in a way photon experiments could not. They did a loophole-free Bell test using superconducting circuits. The two qubits sat about 30 meters apart inside a cryogenic system, entangled through a microwave link. The measurements were fast, and the detection was nearly perfect. The Bell inequality was violated, with no fair sampling assumption, on hardware that is also the foundation of an emerging computing industry. This matters for two reasons that go well beyond physics. The first is independence. Photons live in the regime of optics. Electrons and diamonds live in the regime of solid-state defects. Superconducting qubits live in the regime of microwave electronics. Three completely different physical systems, three completely different sources of possible error, all delivering the same verdict. When nature gives you the same answer in three different languages, the answer is not a translation artifact. The second is control. A photon experiment is a one-shot affair. The photons are made, they are measured, the data is collected. You can change the angles between runs, but you cannot really interrogate the same quantum state twice. A superconducting quantum chip lets you do something the photon people could only dream about. You can prepare a specific state. You can act on it with a sequence of operations. You can measure it however you want. You can ask it a structured question, not just a single yes or no. You can reprogram the experiment overnight. This is where the story tilts, because once you have a programmable quantum machine, the Bell test stops being the only test you can run. Every strange thought experiment that physicists have invented over the last 100 years, every paradox they wrote down to torture each other at conferences, suddenly has a piece of hardware that can actually try it. You can simulate the Wigner's friend, the thought experiment that puts a conscious observer inside a sealed lab. You can simulate the Fraukiger and Renner paradox, the proof that quantum theory cannot consistently describe its own use under certain assumptions. You can simulate local friendliness, the inequality that says one of your favorite beliefs about reality must be wrong. You can run versions of these experiments today on hardware you can rent in a cloud account. That is what is genuinely new. Quantum computers have turned the foundations of physics into something you can poke, not metaphorically, literally, with a control pulse on a chip. Before we walk through what they have already found, we have to be clear about what these machines actually are. Because the words quantum computer carry a lot of mythology, and the actual object is stranger and simpler than the headlines. That fingernail-sized chip is not magic, but the rules it runs on are. Forget the marketing. A quantum computer is not a faster classical computer. It is a different kind of object altogether, running on different rules. A classical computer stores information in bits. Each bit is either 0 or 1. The whole machine is, at any instant, in one specific configuration. A laptop with 1 billion bits is in one of an enormous number of possible configurations, but it is in exactly one of them at any given moment. A quantum computer stores information in qubits. A qubit can be 0, 1, or a quantum combination of both at the same time. That combination is called superposition. It is not metaphor. It is not a fuzzy guess about which value the qubit holds. It is the actual state of the qubit before measurement. Only when you check does the qubit commit to one answer. Two qubits in superposition can be entangled. That means their states are linked. Measure one, and the other instantly behaves as if it knows the result. We met this already with photons. The same effect happens between two qubits on a chip. The link survives even when the qubits are physically separated, as long as the chip stays cold and quiet enough to preserve it. The whole computational trick of a quantum computer is to set up a calculation where the right answer is encoded in patterns of superposition and entanglement across many qubits. You run a sequence of operations called a circuit that nudges the qubit states in the right direction. Then you measure. The act of measurement crashes all that quantum richness down into a classical answer. If the circuit was designed well, the answer that pops out is the one you wanted, with high probability. That is a quantum computer. A controlled cage for superposition and entanglement, with operations that act on those states and measurements that read them out. Now here is the part that matters for our story. The machinery that lets a quantum computer solve problems is the same machinery that makes it a perfect laboratory for testing the foundations of physics. To compute, you need to put qubits in superposition. To run a Bell test, you need to put qubits in superposition. To simulate Wigner's friend, you need to put qubits in superposition and have one of them play the role of an observer inside a sealed lab. The hardware does not care which job you give it. The same chip that runs an algorithm to factor a number can run a circuit that asks whether reality is observer independent. Researchers at IBM, Google, and academic labs have noticed this. Some of them have made it their main job. They book time on the same publicly available quantum hardware that startups use for business applications, and they run circuits designed to test the deepest assumptions of physics. The data comes back as bit strings, just like any other quantum computation. But the meaning of those bit strings is something else entirely. One number above a threshold means objective reality, in a precise technical sense, cannot be saved. The hardware does not know it is delivering a verdict. It just runs the circuit. But the circuit has been carefully built so that the answer it returns is a measurement of something philosophers have argued about for a century. That shift from passive optical experiment to programmable quantum laboratory is what put the foundations of reality on the same hardware as your cloud-rented quantum job. And the first thing those laboratories did was rerun the most famous test in modern physics. This time, on a chip. A Bell test on a quantum computer looks nothing like the Berkeley experiment from 1972. There are no calcium atoms, no fiber spools strung across a campus, no detectors counting photons one at a time. There is a chip in a refrigerator, a control system sending microwave pulses, and a few lines of code. The code does the same job that all those photons and detectors used to do. It prepares two qubits in an entangled state. It applies a chosen rotation to each one, mimicking the choice of measurement angle. It reads out both qubits, it logs the pair of results, then it does this thousands of times, sweeping through different rotation choices, building up the statistics needed to evaluate the Bell inequality. When the run finishes, the data is fed into the same formula physicists have used for 60 years. If the resulting number sits below a specific threshold, local realism survives. If it rises above the threshold, the chip has just confirmed what photons confirmed in 2015. Reality cannot have all the comforting properties Einstein wanted it to have. The number rises above the threshold, reliably, repeatably, on hardware you can rent. This is the part that surprises people the most when they first hear it. A quantum chip is not a special-purpose tool built to test the foundations of reality. It is a general-purpose object that just happens to be the kind of object the test was always made of. Photons in 2015 violated Bell's inequality because photons are quantum systems. Qubits in 2023 violate it for the same reason. The only thing that has changed is that we now control the quantum system instead of merely watching it. The 2023 superconducting result, published in Nature, was not a casual confirmation. It was a deliberate, loophole-free Bell test designed to clear the same bar that the 2015 Photon experiments had set. The two qubits were placed in separate cryogenic systems. The measurement choices were generated by fast, independent, random sources. The detection efficiency on a superconducting qubit, when measured properly, is essentially complete. The result violated the Bell inequality by many standard deviations. For a physicist, that matters because it confirms the result on yet another platform. For everyone else, it matters for a different reason. It means the chips quietly being installed in research labs and cloud data centers are, at the foundational level, behaving in a way that the classical world cannot reproduce. The hardware is not approximating quantum mechanics. It is quantum mechanics. The same strangeness Einstein argued against is now manufactured at industrial scale. There is a strange beauty to this. The same kind of machine that companies hope will one day break encryption, design new drugs, or simulate complex chemistry is, as a side effect, also the most precise courtroom we have ever built for testing whether reality has the properties we assume it does. And the courtroom keeps ruling against the assumption. There is one more thing about doing these tests on quantum computers that the photon experiments could never offer: reproducibility on demand. The 2015 experiments were heroic, one-time runs by world-class teams. The 2023 superconducting test was harder still. But once the technology exists, anyone with a research account can, in principle, repeat parts of it. Bell tests, in slightly less stringent form, have been run on IBM quantum hardware available to the public. Which means the next chapter of this story is being written by groups outside the original elite labs. And one of those groups noticed something in the data nobody was expecting. IBM made a decision a few years ago that quietly changed the texture of foundational physics. They put their quantum processors online and let researchers around the world book time on them. The intent was to grow a software ecosystem. The side effect was unexpected. Small academic groups, with no budget for a fridge of their own, started running experiments on the foundations of reality from their laptops. The results have piled up. Bell tests on IBM quantum hardware have been done many times by independent teams. Some are educational demonstrations, useful for teaching. Others are full statistical investigations with millions of shots, designed to push the experiment as hard as the public hardware allows. The qualitative answer in every case is the same. The quantum chip violates Bell-type inequalities. Local realism does not survive contact with the machine. The quantitative situation is more interesting. On public hardware, the Bell violations are real, but messy. The qubits are imperfect. They suffer from noise, from crosstalk, from small calibration drifts. They are not as clean as the dedicated hardware in a university foundations lab. None of that changes the verdict. The data still climbs above the local realism ceiling. The presence of noise shifts the numbers around it, but does not erase the gap. Then, in 2024, a group looked at something that the gold standard experiments had largely set aside. They tested whether the IBM hardware respects something called the no signaling condition. No signaling is the rule that says a measurement on one entangled qubit should not, in any statistically detectable way, change the outcome distribution at the other qubit. It is the rule that prevents entanglement from being used to send a faster-than-light message. Quantum mechanics predicts that no signaling is exactly satisfied. Most experimental results, within their error bars, agree. On IBM Quantum, in extremely large statistics, the team found a small but persistent violation of no signaling. That is unusual. It does not mean the chip is sending faster than light signals. The much more likely explanation is technical. The qubits on a chip are physically close. Crosstalk, leakage, and shared control lines are real engineering issues. A measurement on one qubit can in principle leak a tiny influence to the other through hardware channels. With enough statistics, those tiny effects show up in the data. The result is not being treated as a discovery. It is being treated as a benchmark. It tells the engineers exactly how clean their isolation is. It tells the Foundation's community that any future loophole-free Bell test on superconducting hardware will need either better physical separation or clever calibration to make sure the no signaling condition is also experimentally enforced, not just assumed. But there is a deeper point sitting in this result. The Bell inequality is meaningful only when no signaling holds. If the two parties can talk, even slightly, the violation can be faked classically. So the same hardware that confirms the spirit of the Bell verdict also reminds us how careful we have to be about the conditions for the verdict to be valid. The story is not as simple as headlines like to make it. Still, the headline survives. On dedicated high isolation hardware, with proper space-like separation, the loophole-free Bell violation is real. On public hardware, it is real, with caveats that the field is openly working on. The verdict is consistent across photons, electrons in diamond, neutral atoms, and superconducting qubits. The classical picture of reality has lost on every platform where the test has been run carefully enough. What none of these tests do, by themselves, is force you to choose which assumption to abandon. Bell tells you that you cannot have all of locality, realism, and free choice. He does not tell you which one to drop. To make that choice harder and stranger, you need a different experiment. You need an experiment that places an observer inside the very system being measured. The small no-signaling violation seen on IBM Quantum deserves a closer look, because it touches a nerve that runs through the whole Foundation's debate. No signaling is the quiet promise that lets relativity and quantum mechanics live in the same house. Quantum entanglement allows distant particles to be perfectly correlated in ways that no classical model can match. But the correlations are only seen after both sides compare notes. Neither side, on its own, can use the entanglement to send a message to the other. That is the no-signaling theorem, and it is the reason quantum mechanics does not contradict the cosmic speed limit. When you actually run a Bell test, you check no-signaling as part of the analysis. You compute the marginal probability that one party gets a particular outcome, averaged over what the other party did. If no signaling holds, those marginals should not depend on the other party's setting. In a clean experiment, they do not. In the IBM Quantum runs at very large statistics, they do by a small but measurable amount. The team that ran the test was careful in their interpretation. They did not claim a violation of relativity. They did not claim a hidden faster-than-light channel. They pointed out that the qubits on a chip are not properly space-like separated. The whole apparatus is small. Microwave pulses travel through shared control wiring. The measurement of one qubit can in principle nudge the readout electronics for another. None of this is mysterious. All of it is engineering. But the data is still notable. It says, in numbers, that the public hardware is not yet behaving as a pristine no-signaling system at the level required for an absolutely clean Bell test. That is a real limit on how strongly the public results can be interpreted. It is also a roadmap for how to improve the next generation. For physicists, this is a useful reminder that the cleanest results in foundations come from purpose-built experiments, not general-purpose chips. The 2023 loophole-free superconducting Bell test was done on a special apparatus designed around isolation. Its results stand. The public hardware results are confirmations in spirit, with engineering footnotes. For the rest of us, the lesson is sharper. The verdict against local realism is robust across multiple platforms. The verdict is not weakened by the engineering noise, but the conversation about what to give up and how to do these tests honestly is still alive. People are still arguing. That is healthy, not weak. Physics works because it argues. Here's what nobody's arguing about anymore. Some classical assumption has to die. The data forbids the comfortable picture in which particles have definite properties before measurement, and nothing reaches across space without a signal. That door is closed. The deeper question is which classical assumption the data forces you to give up. Bell tests do not answer this on their own. They tell you the conjunction of locality, realism, and free choice cannot all hold. They do not tell you which one to release. Different physicists release different beams. Most release realism, accepting that quantum systems do not have predetermined values. Some release locality, accepting that entangled systems are linked across space in some non-signaling but real way. A few release free choice and accept superdeterminism, the most uncomfortable position, because it implies your sense of choosing is part of a deeper script. Each of these positions makes its own predictions for stranger experiments that go beyond Bell, and one of those stranger experiments has now been run. It does not place two particles at opposite ends of a corridor and ask whether they correlate. It places an observer inside a sealed laboratory and asks whether their experience of reality and the outside world's description of it can both be true at once. The answer is harder to swallow than anything Bell ever put on paper. In 1961, the physicist Eugene Wigner published a paper that was meant to be a warning about how strange quantum mechanics gets when you take it seriously. The paper has gone on to become one of the most quietly disturbing thought experiments in the history of science. The setup is simple. Imagine a friend, locked inside a sealed laboratory. Inside the lab, the friend has a quantum particle. The particle is in a superposition of two states. The friend measures it. The friend writes down the result. From the friend's point of view, there is no mystery. They saw a definite outcome. The particle was up, or it was down. They wrote it on a piece of paper. Reality for them is settled. Now imagine you are Wigner, standing outside the sealed lab. You have not opened the door. You have not seen the result. According to the rules of quantum mechanics applied honestly, the entire contents of the lab, including the friend, including the piece of paper, are now in a superposition. The friend who saw up and wrote up, and the friend who saw down and wrote down, are both still part of the quantum state of the lab. From your point of view, no measurement has happened yet. The result becomes definite only when you open the door. This is not a trick. This is what the equations say if you apply them to large systems instead of stopping at the boundary of the experimental apparatus. There is no mathematical line that tells you when to stop treating something as quantum. The smaller the system, the easier it is to keep coherent. The larger the system, the harder. But there is no rule in the equations that says coherence must end at any specific size. So the friend, doing physics inside the lab, says the measurement is over. You, doing physics outside the lab, say the measurement has not happened yet. Two honest applications of quantum mechanics, two contradictory descriptions of the same room. For most of its life, this was just a philosophical puzzle. People shrugged. They said the friend is not really an isolated quantum system. People are warm. They are enormous. They leak heat and air and light. The superposition would collapse immediately through interaction with the environment, a process called decoherence. The friend's experience would line up with yours as soon as any photon left the lab. Crisis averted. That argument was comfortable. It also turned out to be incomplete. Because in 2017, a team of theorists named Fraukiger and Renner showed that you do not need to put a real, conscious friend inside a real lab to find the contradiction. You can construct a more careful version of the thought experiment, with multiple agents, where the contradiction follows from the assumptions of quantum theory, plus a few innocent-seeming ideas about how observers reason. The full statement is technical. The conclusion is sharp. If you assume that quantum mechanics applies universally, that observers can reason about each other consistently, and that there is one single objective outcome to every measurement, you reach a logical contradiction. Translated to plain language, at least one of those three assumptions has to be wrong. That was the theory. In 2019, a team in Edinburgh did something brave. They turned a version of this thought experiment into an actual experiment. Not with people, not with conscious observers, but with photons playing the role of the friend. The experiment used 6 entangled photons arranged so that 2 of them played the part of internal observers inside 2 boxes, and the other 4 were used to test whether the outside picture and the inside picture could be consistently combined. If Wigner was wrong and observer-independent reality holds, the data should fall under a known mathematical ceiling, a Bell-type inequality adapted to this scenario. If Wigner was right, the data should rise above it. The data rose above it, by 5 standard deviations. A piece of philosophy had just given a measurement, and the next chapter would force the rest of us to reckon with what that measurement actually said. The 2019 Edinburgh result is worth sitting with. It does not say that 2 people will disagree about whether the lights are on. It says something narrower and stranger. Under specific quantum experimental conditions, 2 observers, both reasoning correctly, both applying the rules of physics correctly, can record incompatible accounts of the same event. The friend inside the box says, the measurement happened, The result was definite. Here is what I saw. The outside observer says, the measurement has not yet happened. The lab is in superposition. Both possible results are still part of the state. Both are right within their own descriptions. Both descriptions cannot be combined into a single objective story. This is what the Edinburgh team measured, in photons playing the role of observers. The data violated the inequality that observer-independent reality would have to satisfy, by a margin too wide to be statistical noise. Now, there are caveats. The photons playing the role of observers are not conscious. They are not memory-storing systems in any rich sense. The community has been careful about exactly what the experiment proves. It proves that quantum mechanics, applied to systems that act as simple observers, leads to a violation of the assumption that a single objective outcome exists across observers. It does not prove that two human observers in a real experiment would have incompatible memories. The conditions for that scale of test do not yet exist. What it does prove is that the thought experiment is not just words. The structure that Wigner described leads, when realized in any physical system that quantum mechanics governs, to data that cannot be explained by an observer-independent account. The assumption that the world has one shared past, accessible in principle to all observers, is not free. It costs something. The cost is paid in the same currency Bell tests use, a measurable inequality violated by real data. This is the part of the Modern Foundations program that has earned the word horrifying in popular write-ups. The word is dramatic. The reality is calmer, but no less serious. The experiments do not show a cinematic split in reality. They show that one of the assumptions you carry without thinking is, under the right conditions, demonstrably untenable. The relevant assumption has a name: absoluteness of observed events. The idea that when an observation happens, there is one fact about what was observed, the same for everyone who could, in principle, find out. Most of daily life seems to support this. The Edinburgh experiment, on 6 photons, says it cannot be universally true if quantum mechanics is. At this point, you might be tempted to dismiss the result on the grounds that the photons are not real observers. That is a reasonable instinct. The community shares it partly, which is why the next phase of the program is to build experiments where the role of the friend is played by something more substantial, something that more credibly counts as an observer. That is harder than it sounds. The natural candidate is a quantum computer. A quantum computer can be told to measure a particle, store the result, and then itself be measured by a larger system. It can play the role of the friend in a way a single photon cannot. It has memory. It has a record of its own past actions. It can, in a precise technical sense, be modeled as a small agent inside the box. This is exactly what a small set of researchers has begun to do. They are scaling up the friend, 1 qubit at a time, using superconducting hardware. Their goal is not to settle the philosophy. Their goal is to push the experiment up to a level where the friend is harder to dismiss as too small to count. Each step up the size makes the conclusion harder to escape. The number that measures this scaling has a technical name, but it is easy enough to describe in plain language. It measures how observer-like the friend really is. And on quantum hardware, that number has been climbing. To see what the Edinburgh team actually did, picture 6 photons. Arrange them carefully. 2 of them are the central system being measured. 2 more act as the internal records, the friends inside their respective boxes. The remaining 2 complete the entanglement structure. The experimenters set the apparatus so that each friend photon performs a measurement on its assigned system photon. The result is encoded in the friend's polarization. Inside each box, that friend photon is now correlated with a definite outcome. From its perspective, the measurement is done. Outside the boxes, the experimenters do not look at the friends. Instead, they perform a different kind of measurement on each box as a whole. A measurement that, if the box is treated as a single quantum system, can extract information that would be impossible if a definite outcome had truly been recorded inside. By varying the settings of these outside measurements and tallying the joint statistics across both boxes, the team built up the full data table. They then checked whether the data could be explained by any model in which there was a single objective outcome per friend. The outside observer's settings were freely chosen, and the events on one side could not faster than light influence the events on the other. The data violated that combination of assumptions by 5 standard deviations. That is the threshold at which physicists treat a result as a real signal rather than a statistical fluke. The team published the work in 2019. The paper title, in plain phrasing, was an experimental test of local observer independence. The conclusion, written carefully, was that at least one of the assumptions of locality, free choice, or observer independence has to be given up. Just as Bell told us we cannot keep all of locality, realism, and free choice together, this newer test tells us we cannot keep all of locality, free choice, and the existence of one shared objective outcome across observers. The structure is the same. The cost is higher. The Edinburgh result is a single experiment with a small number of photons, and the community has been honest about the limits of how far it generalizes. But it is not the only experiment of its kind. Other groups have proposed and run variations. Some use different particle sources. Some use different inequality structures. The qualitative answer has held up. When you treat any physical system as a simple observer inside a sealed box, the assumption that the box has one single objective fact about what happened becomes incompatible with quantum predictions, and quantum predictions keep matching the data. This is why the title at the top of this video is not pure clickbait. The verdict from the experiments, taken together, is that one of 3 things must be wrong. Either the inside of a sealed quantum lab does not contain a definite outcome the way you would assume, or events can influence each other across space in ways that ignore the speed limit, or experimenters do not really have the freedom of choice they think they have. These are not small concessions. Each one rewrites a piece of common sense. The most popular concession in the community is to soften the idea of one shared, objective fact across observers. To accept that what counts as an event for one observer may not be a definite event for another. This is not the easy answer. It is the answer most working physicists are landing on, because the alternatives are even harder. That landing has consequences. If the observer-dependent picture is right, then reality is something more like a layered network of perspectives that quantum theory stitches together, rather than a single shared movie playing out the same way for everyone. That is uncomfortable. It is also where the experimental signal is pointing. To push the signal harder, the next move is obvious. Make the friend bigger. Make it do more. Make it harder to dismiss. That is what the next generation of quantum computer experiments is trying to do. In 2020, a team of theorists led by Bong and colleagues sharpened the Wigner's friend story into something that looks more like a Bell test. They called the result local friendliness. The name sounds gentle. The content is not. The argument goes like this. Imagine the extended Wigner's friend setup, but now with 2 friends in 2 boxes, each performing measurements on entangled particles, and 2 outside observers performing their own measurements on the boxes. Build the structure carefully. Define a specific inequality on the joint statistics. Then prove a theorem. The theorem says that any physical theory in which 2 assumptions hold, that observed events are absolute, and that the outside choice of measurement does not influence the friend's experience faster than light, must satisfy the local friendliness inequality. Any such theory, quantum or classical, hidden variables or no hidden variables. The inequality is a hard ceiling under the umbrella of these assumptions. Quantum mechanics predicts a violation of that ceiling. When the photonic version of the experiment is run, the data violates it. The cost is now sharper than under the original Bell theorem. Bell forced you to give up at least one of locality, realism, or free choice. Local friendliness forces you to give up at least one of free choice, the locality of the friend's perspective, or the absoluteness of observed events. That last one is the new and difficult cost. It says that an observation, once made by some observer, may not correspond to a single fact that other observers can in principle agree on. For most of human history, this would have sounded like a confused statement. An event happens, or it does not. It happens once, and afterward there is a single truth about what occurred. We may have different memories or accounts, but there was a fact of the matter. Quantum mechanics, applied to its own observers, says that this assumption has a price, and the price has now been paid by real data. The reason this is more disturbing than Bell is that Bell could be absorbed without giving up the idea of a shared past. Most physicists who accept Bell give up either realism or, more rarely, locality. Either way, they keep the idea that whatever did happen, happened once. Local friendliness chips at that final comfort. The community is not unanimous about how to read this. Some interpretations of quantum mechanics already accommodate observer relative facts, like relational quantum mechanics or cubism. Other interpretations, like Bohmian mechanics or many worlds, handle the inequalities by giving up something else, locality in one case and the very idea of a single outcome in the other. The local friendliness experiments do not pick the winner. They narrow the field. They tell us, with measurements rather than arguments, that any future interpretation must pay this cost. The sharpest reaction in the field has not been panic. It has been a slow shift in vocabulary. Where physicists used to say a measurement produces a definite outcome, the more careful ones now say a measurement produces a definite outcome relative to an observer. The word relative is doing more work than it used to. It is not a hedge. It is a result. This shift is also what makes the move to quantum computers so important. The photonic local friendliness tests are powerful but limited, because the photons playing the role of friends are extremely small and simple. The most reasonable resistance to the conclusion is to say, of course, tiny photons cannot really count as observers. The result tells us nothing about real observation. To answer that resistance, you have to make the friend bigger, more structured, more memory-rich, more plausibly observer-like. That is the program now being run on superconducting hardware. The friend, in those experiments, is a quantum computer. A small one, for now, but each new generation of hardware lets the friend grow. In 2024, a group published an experiment that took the local friendliness program out of the photonics lab and into the quantum computing era. Their idea was simple in spirit and difficult in execution. Use a quantum computer to play the role of the friend. The setup, simplified, looks like this. A small region of qubits inside a chip is set aside to act as the friend. This region performs a measurement on a system qubit, then stores the result in its own internal state. From the rest of the chip's point of view, the friend region is now a sealed lab containing a measurement record. The outside observer, also implemented as a circuit on the same chip, then performs a measurement on the friend region as a whole. Some of those outside measurements treat the friend as if it has definitely recorded an outcome. Others treat the friend as if it is still in a coherent quantum superposition, and extract interference information that would be impossible if a real, definite measurement had truly happened inside. By repeating this circuit many times across different settings, the team built up the joint statistics needed to evaluate a local friendliness inequality. The team reported a violation, with caveats about the noise and loopholes inherent in current hardware. But the violation is there, and the size of the friend, the number of qubits playing the observer role, is no longer 1 or 2. It is several. With future hardware, it will be more. This is where the program becomes uncomfortable in a new way. The concept the researchers use to track this growth is called the branch factor. It is a measure of how many independent quantum branches the friend's measurement creates, roughly how observer-like the friend is. A single qubit acting as a friend produces a small branch factor. A small cluster of qubits produces a larger one. As the branch factor grows, the assumption that the friend is too small to count as an observer becomes harder to defend. you can keep dismissing a single qubit. You start to look strained, dismissing a cluster of 50. The team behind the 2024 experiments has been explicit about their goal. They want to keep climbing the branch factor on better and better hardware until skeptics run out of room. At some point, the friend will be a quantum system large enough and structured enough that calling it not an observer requires a special argument. At that point, the local friendliness violation will have been demonstrated against a friend that no honest reading can dismiss. We are not at that point yet. The current experiments are an opening move, but the trajectory matters. For the first time in the history of physics, a thought experiment about the role of observers in quantum mechanics has become a hardware program with a measurable progress metric. The deeper meaning of this is worth saying plainly. A quantum computer is no longer just a machine for computing. It is also a machine for doing experimental philosophy. The same chip that might one day factor large numbers is, today, being used to test whether reality has the property of containing a single shared past. The early returns are consistent with what the Photon experiment said. They say the same thing the Bell tests said. They say the same thing the Edinburgh experiment said. Whatever the world is, it is not the world Newton described. It is not the world Einstein wanted. It is not the world your everyday intuition assumes. The question is no longer whether to give up some piece of that intuition. The question is, which piece? And the experiments, by going further than Bell, have made the most popular escape route harder to take. That escape route had a name in the textbooks. It was called the assumption of free choice. It is the next thing in our story, and it survives every test. It also costs more to give up than most people realize. The branch factor is the quiet hero of the next generation of foundations experiments. It sounds technical. It is actually the most honest measurement we have of how seriously we should take the friend inside the box. Picture it this way. When a quantum measurement happens, the measuring system splits into branches, one for each possible outcome. A coin flip produces 2 branches. A simple qubit measurement produces 2 branches. A more complex measurement, performed by a system with internal structure that records and remembers, produces a branch for every distinguishable internal state the recording can take. The richer the recorder, the more branches. The more branches, the more the recorder behaves like a real observer rather than a passive marker. That, roughly, is what the branch factor tracks. A photon playing the role of the friend has a branch factor close to the minimum. It records a measurement outcome, but it does not store anything else. There is no internal memory beyond the result. A skeptic can reasonably say, this is not an observer in any meaningful sense. It is a marker. The local friendliness violation tells us something about markers, not about observers. A quantum computer playing the role of the friend can have a much higher branch factor. The friend region can store the result. It can also store auxiliary information about the measurement process, the time it occurred, the path taken through the circuit. Each piece of stored information multiplies the number of distinguishable internal states. The friend starts to look less like a marker and more like a small, primitive observer with a record of its own actions. The 2024 program, run on superconducting hardware, has been explicit about climbing this number. Each new generation of experiments uses a friend region with more qubits and more internal structure. Each new generation reports a local friendliness violation at a higher branch factor than the last. The trajectory is clear. The destination is a point where the friend has so much internal complexity that calling it not an observer requires special pleading. We are not there yet. The branch factors achieved so far are small by any human standard. A friend region of a few dozen qubits is not a person, not even close, but the climb has started, and the progress on quantum hardware in the last decade suggests it will continue. What makes this program meaningful, beyond the foundation's question, is that it does not rely on philosophical argument. It relies on hardware capability. Every step up in qubit count and coherence time is a step up in the strength of the conclusion. The argument is not, quantum mechanics is strange, and therefore reality is observer-dependent. The argument is, here is a measurable inequality, here is a friend with this much internal structure, here is the data, the inequality is violated, please tell us why the friend does not count. The most likely outcome over the next decade is that the friend will keep getting larger and the violations will keep being reported. At some point, the community will face a clear choice. Either accept that the assumption of one shared objective past must be modified, or commit to a specific argument about why a quantum friend of a certain size still does not count as an observer. The second option requires drawing a line. Where is the line? What is on each side of it? Why is your line at that place? These are not easy questions, and the field has resisted answering them for decades. The branch factor program is, in effect, forcing the question. And forcing the question is exactly what theory had failed to do for 100 years. In 2018, two researchers at ETH Zurich published a paper that quietly shook the Foundation's community. Daniela Frautschiger and Renato Renner had constructed a thought experiment more careful than Wigner's original. They proved a theorem. The theorem says, in plain language, that if you assume quantum mechanics applies universally, that observers can reason consistently about each other using quantum theory, and that every measurement has a single objective outcome, then you can derive a logical contradiction. That last sentence deserves to be read twice. The contradiction is not a fuzzy paradox, it is a hard logical inconsistency. Two agents in the experiment, both using the rules of quantum mechanics correctly, both reasoning about each other's reasoning correctly, reach predictions about the same future event that cannot both be true. To see why this matters, consider what each of those three assumptions means. Universal applicability means quantum mechanics governs all physical systems, including observers. Consistency between observers means that if I know you have applied a sound argument and reached a conclusion, I can take that conclusion as true myself. Single objective outcomes means every measurement produces one definite result, the same one for everyone who can in principle find out. Each assumption sounds reasonable in isolation. Each one is held by some serious interpretation of quantum mechanics. The Frautschiger and Renner result says they cannot all be held at once. The construction itself is elaborate. It involves 4 agents. 2 are inside sealed labs, performing measurements. 2 are outside, performing measurements on the labs. Each agent uses the standard rules of quantum mechanics to predict the outcomes other agents will see. By chaining their reasoning together, the agents reach a situation where one of them confidently predicts an outcome of one type, while another, equally confident, predicts an outcome of a different type. And quantum mechanics says both predictions must be made with the same probability of being correct. Run the scenario many times. The contradiction shows up in the statistics. Some fraction of the runs produces an outcome that one agent's reasoning had ruled out as impossible. The paper provoked a long debate. Critics argued with some force that one of the agents was applying the rules incorrectly, or that the situation was not really self-consistent in the way the authors claimed. Defenders argued, also with force, that the construction was sound and the conclusion stood. The dust has not fully settled. What has emerged is a consensus that, however you slice the argument, you have to give up at least one of the 3 assumptions, and giving up any one of them costs something dear. If you give up universal applicability, you have to draw a line somewhere in the universe and say, on this side quantum mechanics, on the other side something else. Nobody has found that line, and most physicists are deeply uncomfortable with the idea that the line exists. If you give up consistency between observers, you have to accept that another physicist, applying quantum mechanics correctly to a system you cannot see, may reach conclusions you cannot trust, even when their reasoning is sound. That is corrosive to the whole practice of science. If you give up single objective outcomes, you accept the observer-dependent picture that the Wigner's friend experiments have been pointing at all along. Most working physicists, faced with this menu, choose the third option. Fraukiger and Renner did not force them to. The Wigner's friend experiments did not force them to. But the combined weight of the theoretical argument and the experimental data is now considerable. The next chapter looks at what each of those three options actually costs. Because choosing one is not a matter of taste, it is a commitment about what kind of universe you live in. By this point in the story, three assumptions have been on the table from the beginning. Locality. The rule that nothing crosses space without a signal at finite speed. Realism. The rule that things have properties before they are measured. Free choice. The rule that experimenters select their measurements without their selections being secretly correlated with the systems they measure. The Bell theorem and its experimental confirmation tell us that these three cannot all be held at once. The local friendliness theorem and its confirmation tell us that absoluteness of observed events, the rule that a measurement produces one shared fact, cannot be held alongside locality and free choice. The Fraukiger and Renner theorem tells us that universal applicability, observer consistency, and single outcomes cannot all hold together. These are three different no-go theorems. They cut into the same wood from three different angles. The combined effect is to leave you with a small set of forced choices. You can give up locality. This is the move associated with Bohmian mechanics and other hidden variable theories. The price is that there is, somewhere in the world, a real instantaneous connection between distant entangled particles. You cannot use it to send messages, but it is there. Relativity, in its strict sense, becomes an emergent rather than fundamental principle. Many physicists find this uncomfortable. The math works, but the picture rubs against everything else we know about how the world is structured. You can give up realism in the strong sense. This is the most popular move, associated with most flavors of the Copenhagen interpretation and its descendants. The price is that quantum systems do not have definite values for most of their properties before measurement. The blur Einstein hated is the world. Properties are produced by measurement, not revealed by it. Your everyday picture of objects sitting around with their own attributes, whether you look or not, is a useful approximation that breaks down at small scales. You can give up free choice. This is the move associated with superdeterminism, defended by a small but serious group, including the late John Bell himself, who took it seriously, even though he did not endorse it. The price is that the universe is set up in such a way that the apparent randomness of measurement settings is secretly correlated with the particles being measured. Your sense of choosing is a feature of a deeper deterministic structure that includes both you and the particles in one tight package. You can give up absoluteness of observed events. This is the move associated with relational quantum mechanics, qubism, and any interpretation that treats facts as relative to observers. The price is that what counts as a definite outcome depends on the observer. There is no single shared past that all observers can, in principle, agree on. Different observers may have different valid descriptions of the same event. You can give up single outcomes entirely. This is the many worlds interpretation. The price is that every measurement produces every possible outcome, in different branches of the universal wave function, and the appearance of a single outcome to you is just the experience of being one branch of the larger structure. The universe becomes much, much larger than it looked. You become much smaller within it. Each of these choices is internally consistent. Each one matches all the experimental data. None of them is obviously crazy. All of them are deeply uncomfortable. The point is not which one is correct. The point is that the comfortable picture, the one in which the world has definite properties, distant events do not influence each other, observers freely choose, measurements produce one shared fact, and there is one objective past, is no longer on the menu. The date has taken it off the menu. You must order from the remaining list. The next 3 chapters walk through what happens to your sense of the world when you commit to each of the 3 big options, starting with locality. Because giving up locality is not what most popular accounts assume. Locality is the assumption that the universe respects distance. If something happens here, Its effects propagate outward at finite speed, capped by the speed of light. Nothing here can poke something there without sending a messenger that obeys the cosmic speed limit. This is not a metaphysical preference. It is the structural rule that makes Einstein's theory of relativity work. Drop locality and you have to rework the relationship between space, time, and causation in ways most physicists are deeply reluctant to attempt. Yet the data forces the question. The Bell experiments have shown, repeatedly, that distant entangled particles produce correlations stronger than any local theory can explain. Either those correlations are produced by some process that ignores the speed of light, or particles do not have the definite properties that would have made local explanations possible in the first place. Most working physicists take the second route, give up realism instead. But a minority takes the first route, and their reasoning is worth understanding. The version of giving up locality that has the cleanest mathematical structure is Bohmian mechanics. In this picture, particles are real. They have definite positions at all times. They follow trajectories. The blur of quantum mechanics is replaced by a hidden wave that guides the particles, and the wave responds instantly to measurements anywhere in the universe. The instant response is the part that breaks locality. When you measure one particle of an entangled pair, the guiding wave updates everywhere at once, including at the location of the distant partner. The other particle's trajectory adjusts accordingly. The correlations seen in Bell tests come out exactly right, because the guiding wave is doing the coordinating across space. This sounds dramatic, and it is, but Bohmian mechanics is mathematically equivalent to standard quantum mechanics for all measurable predictions. You cannot use the instant connection to send a faster-than-light message. The randomness of quantum measurements in Bohmian language comes from the fact that you do not know the exact starting positions of the particles. The hidden positions are real, but unknowable. So you get the same statistical predictions as standard quantum mechanics, with a different ontology underneath. The cost of this picture is significant. The guiding wave lives in a high-dimensional space, not in the ordinary three-dimensional world. Special relativity has to be treated as an emergent feature of the statistics, not a fundamental rule. Most attempts to extend Bohmian mechanics to relativistic quantum field theory have struggled. The picture works beautifully for non-relativistic quantum mechanics, and becomes much harder when you try to incorporate the rest of physics. A related move is the broad family of non-local hidden variable theories. They all share the feature that some kind of non-local connection coordinates distant correlations, while keeping particles real with definite properties. Different versions handle the connection differently. None of them have produced predictions that differ from standard quantum mechanics in any test that has been run. What you gain by giving up locality is realism. You keep the comforting idea that things have properties whether you measure them or not. You keep the idea that there is a single, definite, objective state of the world at every moment. You keep your common sense ontology. The world is solid, and reality is one shared movie. What you give up is the idea that distance matters in the way you thought it did. The two distant particles are not really distant in the sense that counts. They are connected by a thread that physics has not fully described, but that nature uses to keep their statistics correlated. For some thinkers, this is a perfectly acceptable trade. The instantaneous connection is hidden, untouchable, undetectable as a signal. It does not let you do anything practical. It just sits in the background, doing the bookkeeping that quantum mechanics needs done. For most working physicists, it is a trade they decline to make. The next chapter is about the trade they accept, giving up realism. And it is more disorienting than it sounds. Realism is the assumption that the world contains definite properties, whether anyone is measuring them or not. The electron has a position. The photon has a polarization. The cup has a temperature. These properties are out there, baked in, regardless of observation. Quantum mechanics, taken at face value, denies this. A particle in superposition does not have a definite value for the property in question. It has a state that encodes the probabilities of various measurement outcomes, but no single outcome is actually present until a measurement is made. The act of measurement does not reveal a hidden value. It produces a value that did not exist beforehand. This is the move most working physicists have made. They have given up realism in the strong sense and accepted that the blur is real. It is harder to swallow than it sounds. Take an electron in a particular quantum state, prepared so that a measurement of its spin along the vertical axis is guaranteed to come out up. Before the measurement, you can confidently say the electron's vertical spin is up. That property is definite. So far, so reasonable. Now ask about the electron's spin along the horizontal axis. Before any measurement, the answer is not that it is right, or that it is left, or that it is some specific in-between value. The answer is that the electron does not have a definite horizontal spin at all. Measure it, and you will get either right or left, with calculable probabilities. But the value did not exist before the measurement. It came into being as the measurement happened. This pattern generalizes. Most properties of most quantum systems are not definite most of the time. Quantum mechanics is mostly about systems that do not have most of the properties you might want to attribute to them. Definiteness is the exception, not the rule. The reason this is the most popular escape from the Bell verdict is that it preserves locality. Distant correlations are not produced by any signal between the particles. They are produced by the fact that the particles are not carrying preloaded answers in the first place. When you measure one and get a result, the result was not pulled out of a hidden store. It was generated. And the result on the other side is generated in a correlated way by the structure of the entangled state, not by any communication. This sounds clean. It is, mathematically. But it costs something philosophical. It costs the idea that there is a definite world out there waiting to be discovered. The world in this picture is partly created by the act of measurement. The properties you see in your experiments are real, but they are not pre-existing. They are co-produced by you and the system. For Einstein, this was unacceptable. He famously asked whether the moon exists when nobody is looking. He was being only half rhetorical. The everyday objects we see around us are kept in their definite states by constant interaction with their environment, a process called decoherence, which mimics the effect of constant measurement. The moon, bathed in sunlight and gravitational interactions, behaves as if it always has definite properties. But isolated quantum systems, kept in a fridge, away from interactions, do not behave this way. They sit in superposition until someone or something forces them to commit. This is the picture most physicists work with. Quantum systems do not have most of their properties until measurement. The classical world emerges from the quantum world through the constant pressure of decoherence, which makes superpositions practically impossible to maintain at large scales. Definiteness is a phenomenon, not a foundation. The price is the loss of an old kind of solidity. The world is real, but its definiteness is local and produced, not universal and given. For many people, this is bearable. The math works, the technology runs, the practical world is unchanged. But there is a third option still on the table, and this one cuts at something even deeper than realism. It cuts at the part of you that decides what to measure in the first place. Free choice is the assumption that the experimenter, when selecting the measurement to perform, makes that selection in a way that is independent of the system being measured. The selection is not secretly correlated with the particles. The settings of the apparatus are chosen freely, in a sense that science has always taken for granted. Without free choice, the whole logic of Bell tests collapses. The reason quantum correlations are surprising is that they exceed what any local theory could produce, given that the experimenters chose their measurements freely. If the choices were not free, if some hidden variable in the world had prearranged the measurements and the particles together, the correlations would no longer be mysterious. They would be a consequence of the conspiracy. This is the position called superdeterminism. It is the most uncomfortable of the three options because it implies your sense of agency is part of a deeper script. Superdeterminism does not say that you are not making choices. It says that the choices you make, including the apparently random ones generated by random number generators or quasar light, are correlated with the systems you measure through some shared causal history. The universe is set up such that the measurement settings and the particle properties are entangled by their common past. This sounds paranoid. It is also the only option that can rescue local realism from Bell. Some serious physicists, including the late John Bell, took it seriously without endorsing it. A handful, most prominently the theoretical physicist Sabine Hossenfelder and a small group of collaborators, have argued in recent years that superdeterminism deserves more attention than it gets. Their argument is simple. The other options ask you to give up something concrete. Locality is a structural rule of relativity. Realism is a foundation of how we describe the world. Single outcomes is a foundation of how we describe events. Each option costs a piece of physics or metaphysics. Superdeterminism asks you to give up something that is, the argument goes, not actually well defined to begin with. The notion that experimenters' choices are statistically independent of everything else in the universe is a strong assumption, not an obvious one. The cost, in their view, is just admitting that the universe is more deeply correlated than we thought. Critics push back hard. They argue that superdeterminism makes the practice of science incoherent. If the universe is conspiring to correlate measurement settings with measurement outcomes, why does science work at all? Why are the patterns we see in nature not arbitrary? The defenders answer that the correlations are highly specific and only show up in carefully designed experiments like Bell tests. Most of physics is unaffected. Cosmic Bell tests have tried to push back on superdeterminism by using light from distant quasars to set the measurement angles. The idea is to source the randomness from astronomical events that are causally disconnected from the source of the entangled particles. If the measurement angles come from light emitted billions of years ago, in different directions, by separate sources, the chain of common causal influence between the angles and the particles would have to stretch back to the very early universe. Several such experiments have been done. They confirm Bell violations. To preserve superdeterminism, you have to accept that the correlation goes all the way back. The Big Bang itself set up a conspiracy that links the photons coming from distant quasars to the entangled particles in your lab today. This is a serious commitment. Some defenders are willing to make it. Most physicists are not. The free choice debate remains the most fragile part of the Foundation's conversation. It is not closed. It cannot be closed by any experiment, because any experiment relies on freely chosen measurement settings to be interpretable, and superdeterminism is precisely the position that denies this. Whatever you give up something serious. There is one more piece of strangeness that deserves a chapter of its own, because it has confused popular accounts of quantum mechanics for decades. It involves an experiment that looks, at first glance, like the future is reaching back to edit the past. It is not that, but it is also not nothing. In 1999, a team led by Yoon Ho Kim performed an experiment that has been quoted, misquoted, and dramatized for the last quarter century. The setup is called the delayed choice quantum eraser. The popular description sounds like science fiction. The actual physics is stranger and more careful than the popular description. The experiment goes like this. Send a photon through a double-slit apparatus, the classic setup that produces an interference pattern when the photon's path through the slits is unknown, and a clump pattern when the path is known. Now, arrange things so that a second photon, entangled with the first, carries information about which slit the first photon went through. By measuring the second photon, you can choose whether to know or not know the first photon's path. The strange part is the timing. The first photon hits its detector first. Its position is recorded. Only later, sometimes much later, is the second photon measured. At that later moment, the experimenter chooses whether to extract the path information from the second photon or to erase it. If the path information is extracted, the data from the first photon, sorted by which slit it came through, shows clump patterns, no interference. If the path information is erased, the data from the first photon, sorted in a different way using correlations with the second photon, shows interference patterns. The dramatic reading is that the choice made later, after the first photon has already been detected, somehow determines what the first photon did at the slits. The future has edited the past. This reading is, by careful consensus, wrong. Here is what is actually happening. The first photon's detector records a long stream of detections, with positions all over the screen. There is no overall interference pattern in that raw data. There is no overall clump pattern either. There is just a smear of positions. Only when the data is sorted using the results of the second photon's measurement do patterns appear. When the experimenter chooses to extract path information from the second photon, the sorting reveals clumps. When the experimenter chooses to erase the path information, a different sorting reveals interference. The patterns are extracted from the same raw data, just by partitioning it differently. The future is not editing the past. The future is choosing how to look at the past. The interference pattern was there, hidden inside the raw data, all along. So was the clump pattern. The two are different views of the same underlying entangled state. The experimenter's later choice picks which view to extract. The mistake in the dramatic reading is to imagine that the first photon's behavior at the slits was changed by the later measurement. It was not. The first photon's behavior was always the result of its participation in the entangled state. The entangled state itself does not localize the photon's behavior to one slit or another, because the photon's behavior was never that simple to begin with. This careful reading has been worked out by many physicists over the years. It is the consensus reading. The delayed choice quantum eraser is not evidence of retrocausality. It is evidence that quantum systems do not have definite properties of the kind classical intuition expects, and that what looks like a paradox is the result of imposing classical thinking on a quantum situation. A small minority of physicists do take the result as suggestive of some genuinely retrocausal structure to nature. They argue that giving up the assumption that causes precede effects, in some carefully limited sense, might offer a cleaner account of certain quantum phenomena. This is a minority view. It is not crackpot, but it is not mainstream. The more important lesson for our story is that quantum experiments routinely look paradoxical to classical eyes. The paradox dissolves when you give up the right classical assumption. The challenge is figuring out which assumption to give up. The next chapter is about the largest and strangest of the responses to this challenge. The interpretation that saves locality, realism, and consistency by paying a price, most people find unbearable. The mainstream response to the delayed choice quantum eraser is that it is not retrocausal. The patterns that appear when the data is sorted by the second photon's measurement were always implicit in the entangled state. The later measurement does not change the past. It selects a way of partitioning records that were already determined. This explanation is mathematically clean. It uses only the standard formalism of quantum mechanics. It does not require any signals to travel backward in time. It is the explanation that appears in most modern quantum optics textbooks. It is what you will hear from working quantum physicists if you ask them at a conference. The minority view is more subtle. It does not claim that information physically travels backward in time. It claims that giving up the classical assumption that causes always precede effects. Or more carefully, that probability distributions over hidden variables are independent of future measurements, might offer a more satisfying account of certain quantum patterns. This minority position is sometimes called retrocausal quantum mechanics. It is associated with theorists like Hugh Price and Ken Wharton, among others. They argue that retrocausal models, carefully constructed, can recover the predictions of quantum mechanics while keeping a locality intact. The cost is giving up an assumption called statistical independence, which is closely related to the free choice assumption we discussed in the superdeterminism chapter. The retrocausal minority and the superdeterminist minority share a common feature. Both want to preserve locality. Both are willing to pay for it by relaxing some assumption about the relationship between measurement settings and the world being measured. They differ in how they do it. Superdeterminism says the correlation comes from a shared past. Retrocausality says the correlation comes from influence flowing backward from the measurement to the source. Neither view has won broad acceptance. Most physicists find both of them too costly compared to giving up realism. But the existence of these views matters because it shows that the response to the Bell verdict is not unique. Different physicists, looking at the same data, choose different beams to cut. The delayed choice experiments are particularly relevant here because they are among the cleanest cases where the question of causal direction in quantum mechanics becomes pressing. A retrocausal interpretation has natural language to describe what happens. A standard interpretation has to insist that the patterns were always present and that only the sorting is new. Both interpretations match the data. The difference is in the picture each one paints. For our story, the takeaway is that the delayed choice experiment is not, on its own, evidence that the future controls the past. It is evidence that quantum mechanics does not respect classical intuitions about causal flow. The same data can be described by interpretations that keep classical causal structure intact, at the cost of giving up realism, and by interpretations that loosen causal structure, at the cost of keeping a more concrete picture of particles and properties. This brings us to the largest of all the interpretations, the one that saves locality, realism, and observer consistency by saying yes to all of them, and paying for the package by accepting that every measurement creates a new branch of the universe. The many worlds interpretation has long been treated as fringe by some and obvious by others. The recent foundational work has not settled the argument, but it has changed the texture of the debate. Many worlds is no longer easy to dismiss because the alternatives have all become more uncomfortable than they used to be. It deserves its own chapter. The many worlds interpretation was proposed by Hugh Everett in 1957, in his doctoral thesis. It was largely ignored for decades. In recent years, it has gained ground, partly because the alternatives have become harder to defend, and partly because the rise of quantum computing has made the formal structure of the interpretation more familiar to working physicists. The idea is to take quantum mechanics literally, all the way up. There is no collapse. There is no special role for measurement. The universal wave function evolves smoothly, according to the Schrödinger equation, forever. Every interaction that quantum mechanics describes as a measurement is actually an entanglement between the system being measured and the measuring device. The combined system enters a superposition of all possible outcomes, with each outcome correlated with a corresponding state of the measuring device. When you, as the observer, interact with the measuring device, you become part of the entangled superposition. There are now branches of the universal wave function in which you saw outcome up, and branches in which you saw outcome down. Each branch is internally consistent. Each branch contains a version of you who remembers seeing one specific outcome, and is convinced that outcome was the real one. There is no collapse because no collapse is needed. The appearance of a single outcome is the experience of being one branch within the larger structure. This picture saves several things at once. It saves locality, because all the dynamics are local within each branch. It saves realism, because the universal wave function is taken to be real. It saves observer consistency, because observers in the same branch agree about what happened. It saves the unitary evolution of quantum mechanics, because nothing is ever discarded. What it costs is breathtaking. It costs the existence of a single world. The universe, in this picture, is a constantly branching tree of histories. Every time a quantum measurement happens, anywhere, The relevant branch splits into branches corresponding to each possible outcome. The branches do not interact with each other in any practical way, but they all exist. The total number of branches grows astronomically with every passing moment. It costs the idea that you are a single person with a single past. There are many copies of you, in many branches, all of whom remember being the one continuous person who lived your particular history. From inside any one branch, the picture is normal. Looking at the structure from outside, if you could, the picture is a vast and growing tree of versions. It costs the simple meaning of probability. In the many worlds picture, every outcome happens. So what does it mean to say a particular outcome had a certain probability? This is called the probability problem in many worlds, and it has spawned a substantial literature. Various solutions have been proposed, none universally accepted. The interpretation works, but how to interpret quantum probabilities within it remains contested. What you gain is consistency. The Frackiger and Renner paradox, which assumes single outcomes, does not apply in many worlds because there are no single outcomes. The Wigner's friend conundrum dissolves because the friend and the outside observer are simply in different parts of the branching structure. The local friendliness violations are accommodated naturally because absoluteness of observed events fails by design. This is what makes the many worlds picture attractive to many theorists. It eats every paradox quantum mechanics throws at it, simply by accepting that all outcomes happen. Critics call this an extravagance. The interpretation introduces an enormous amount of unobservable structure to solve problems that other interpretations solve with smaller commitments. Defenders call it parsimony. The interpretation introduces no new entities beyond the wave function itself, which all interpretations have to take seriously. The disagreement is about which kind of simplicity counts. Whatever you think of many worlds, it is no longer easy to dismiss. The recent Foundation's work has made it one of the cleanest available options. The price is high. The price for every other option is also high. There is no cheap interpretation of quantum mechanics anymore. Of all the moves available to defenders of classical reality, the strangest is the one that simply refuses to be tested out of existence. Superdeterminism cannot be falsified by any Bell test, because Bell tests assume the very thing superdeterminism denies: free choice of measurement settings. This is not a flaw in Bell tests. It is a feature of the logical structure of the question. Any experiment designed to test correlations between distant particles has to assume the experimenters chose their settings independently of the particles. Without that assumption, the math does not work. So superdeterminism, by denying the assumption, sits outside the reach of the tests. Some physicists treat this as a fatal weakness of the position. They say that if a theory cannot be falsified by any experiment, it is not a scientific theory. Defenders of superdeterminism push back. They argue that the position can be tested in indirect ways by looking for the kinds of correlations between measurement settings and physical systems that the theory predicts. So far, no such correlations have been found, but the search is ongoing, and the structure of the predicted correlations is subtle. The position has a long pedigree. John Bell himself took it seriously. He did not endorse it, but he saw as the only loophole in his own theorem that could not be closed by experimental ingenuity. The cosmic Bell tests, which use light from distant quasars to set measurement angles, push the required conspiracy back in time but do not eliminate it. To preserve superdeterminism, you have to accept that the conspiracy was set up at the very beginning of the universe. This is where it stops being a comfortable position. The Big Bang, in the superdeterminist picture, was tuned to correlate the future paths of all particles with the future settings of all experiments. The early universe contained the seeds of the apparent randomness we see in our laboratories today. Nothing in this picture violates the laws of physics. It just requires the laws to have very specific initial conditions. Some defenders argue that this is no stranger than the fine-tuning required for the universe to support life. Many physicists, faced with the apparent fine-tuning of physical constants, accept that some kind of selection or constraint operates at the cosmic scale. Superdeterminism in this framing is just one more form of cosmic scale constraint. The universe is more correlated than we thought, but that is not, in itself, an argument against it. Critics counter that this kind of reasoning makes science incoherent. If the measurement settings and the systems being measured are correlated, why do we trust any experimental result? Why does science work? Defenders answer that the correlations are precise and limited. They show up in carefully designed bell-type experiments. They do not affect the broad practice of science, which deals with statistically robust patterns that do not depend on the freedom of individual measurement settings. Where this leaves us in the year 2026 is with superdeterminism as a live but unpopular position. A few serious thinkers defend it. Most physicists ignore it. The experiments that would test it are difficult to design because the theory is precisely structured to evade bell-type tests. For our story, the importance of superdeterminism is what it tells us about the shape of the problem. Even with all the experimental progress of the last 60 years, even with loophole-free bell tests on multiple platforms, even with local friendliness violations on quantum computers, there remains one logical escape from the experimental verdict. That escape requires giving up free choice. It requires accepting a deeply correlated universe. Some people are willing to make that trade. Most are not. The data alone cannot force the choice. The data narrows the choice to a small set of unpalatable options. Each one costs something dear. Each one rewrites a piece of common sense, which brings us to the option that the experiments seem to be pushing the field toward, slowly and reluctantly. The option that says reality itself is not a single shared movie, but a network of perspectives. The combined weight of the Bell tests, the Wigner's friend experiments, the local friendliness violations, and the Fraukiger-Renner argument is pushing many physicists toward a conclusion they would not have entertained 20 years ago. Reality, in the strict sense, may be observer-dependent. This needs to be said carefully. It does not mean reality is in your head. It does not mean different people see different things and there is no common world. It means something narrower and stranger. Under specific quantum experimental conditions, the assumption that there exists a single objective fact about what happened, accessible in principle to all observers, becomes incompatible with the data. The technical name for this conclusion in the Foundation's literature is the failure of absoluteness of observed events. The plain language version is that what counts as a definite event for one observer may not be a definite event for another, when the observers are themselves quantum systems being measured by larger observers. This is not the same as relativity. In relativity, different observers can disagree about the timing or the order of events, but they all agree on what events happened. In the observer-dependent picture suggested by the Foundation's experiments, observers can disagree about whether an event happened at all, in the strong sense that they can both be right within their own frameworks, and yet have incompatible accounts that cannot be combined into a single shared story. If this picture is correct, the universe is not a single movie playing out for everyone to watch. It is something more like a network of consistent perspectives, each internally coherent, stitched together by quantum correlations that make sure the perspectives never disagree in any way that would let you exploit the disagreement. This is the hardest of the conclusions to absorb. It does not match anything in your daily experience. The reason it does not is that decoherence, the constant interaction of large systems with their environment, makes it practically impossible to set up the conditions under which the observer-dependent effects show up. Two friends in a normal room doing normal physics will agree about everything that happened. The disagreements only show up under specifically engineered quantum experimental conditions, where one friend is sealed inside an isolated lab and the outside world is doing quantum measurements on the lab as a whole. For everyday purposes, the world looks objective. Decoherence enforces a kind of practical objectivity that makes daily life possible. The point of the Foundation's experiments is that this practical objectivity is emergent. It is a feature of how large, warm, interactive systems behave. It is not a feature of the underlying physics. At the underlying level, observer dependence is real, and it shows up when you set up systems carefully enough to keep them coherent. The implications are still being worked out by physicists and philosophers. Some interpretations of quantum mechanics, like relational quantum mechanics and cubism, embrace observer dependence as a fundamental feature. They argue that quantum theory is essentially a theory of relative facts, and that trying to construct an absolute account of events is a misunderstanding of what the theory is for. Other interpretations, like many worlds, dissolve the question by accepting that all outcomes happen, and that the appearance of single outcomes is itself an observer-dependent phenomenon. What none of the major interpretations can do anymore, given the data, is preserve the comfortable picture in which there is one objective story of the world that all observers can, in principle, agree on. That picture is gone. What remains is the question of how to live with its absence. And one of the strangest realizations of the Foundations program is that quantum computers, the same machines being built to solve practical problems, are also the natural laboratories for exploring the structure of what replaces it. A quantum computer can simulate any quantum system, in principle. This includes systems that contain observers performing measurements on other observers. It includes Wigner's-Friend setups, Frauchiger-Renner scenarios, local friendliness experiments, and any other thought experiment whose participants can be modeled as quantum agents. This capability is not abstract. Several research groups have already implemented these scenarios on quantum hardware. The implementations are necessarily simplified. The agents are small, the friends are not conscious, the loopholes are not all closed. But the structures are real, and the results match the theoretical predictions. The Frauchiger-Renner thought experiment, in particular, has been simulated on quantum computers. Researchers at ETH Zurich and elsewhere have built software frameworks specifically designed to model multi-agent quantum scenarios on quantum hardware. The agents are quantum circuits. The measurements are quantum operations. The reasoning of one agent about another agent's reasoning is encoded in the entanglement structure of the circuit. The contradictions that the theorem predicts show up in the statistics of the runs. This is a new kind of physics. For most of its history, physics has worked by writing down theories and then designing experiments in the natural world to test them. The experimenters do not choose the systems. They find the systems and try to ask them questions. With quantum computers, the experimenters now design the systems themselves, including systems that could not exist naturally because they are too fragile to survive in a non-laboratory environment. The thought experiments of quantum foundations were, for a century, untouchable by experiment because the systems they described could not be assembled. Wigner's-Friend required a sealed conscious observer in a perfectly isolated lab. Frauchiger and Renner required 4 agents reasoning about each other's reasoning under specific quantum conditions. None of these scenarios could be built in the physical world. Quantum computers can build them. Not at the scale of conscious observers, not yet, but at the scale of quantum agents with internal memory and reasoning capacity. The scale is small, but it is real, and it is growing with hardware capability. The implication for the Foundations program is profound. Thought experiments that were once treated as philosophical exercises, useful for clarifying concepts but not for testing physics, have become testable on actual hardware. The contradictions they predict can be observed in the data. The interpretations of quantum mechanics that handle the contradictions differently can, in principle, be distinguished by the patterns they predict in carefully designed quantum simulations. The community has not yet reached the point where any interpretation has been definitively confirmed or ruled out by these simulations. The hardware is too noisy, the loopholes are too many, but the program is underway, and the trajectory is clear. Quantum computers are becoming a tool for distinguishing between interpretations of quantum mechanics, not just a tool for computing. This is a quiet revolution in how foundational physics is done. For most of the 20th century, debates about the interpretation of quantum mechanics were considered impossible to settle by experiment. The interpretations all made the same predictions for any experiment that could be done. They differed only in the stories they told about what was happening underneath. The experiments of the last decade have changed that. Interpretations that disagree about the role of observers can be distinguished by local friendliness tests. Interpretations that disagree about the consistency of multi-agent reasoning can be distinguished by Frauchiger-Renner-style experiments. Interpretations that disagree about the existence of single outcomes can, in principle, be distinguished by branch factor experiments at large enough scale. The Foundation's community is no longer just arguing, it is testing. And the tests, so far, have been pulling the field steadily away from the comfortable interpretations and toward the uncomfortable ones. In October 2022, the Royal Swedish Academy of Sciences awarded the Nobel Prize in Physics to Allan Aspect, John Clauser, and Anton Zeilinger. The official citation reads, "For experiments with entangled photons, establishing the violation of Bell inequalities, and pioneering quantum information science." The technical phrasing covers the substance. The three laureates spent decades demonstrating that the quantum predictions for entangled particles violate Bell's inequalities, and that the violations cannot be explained by local hidden variable theories. Their work, taken together, closed the major experimental loopholes and established the foundations of quantum information science. What the citation does not say, but what the work means, is that the comfortable classical picture of reality has been formally ruled out. The Nobel Committee, in awarding the prize for work establishing the violation of Bell inequalities, was acknowledging that local realism is not a viable description of the physical world, not as a working assumption, not as a fallback. The data has settled it. The committee, of course, did not phrase it this way. Nobel citations are conservative by design. They describe what was done, not what it means. The meaning has to be read in the context of the work itself. Read that way, the citation is one of the more consequential statements the committee has made in physics. It elevates a question that physicists once considered too philosophical to test into the highest scientific recognition the world offers. It tells the broader scientific community and the public that the Foundation's work matters, that the experiments were not idle, that the verdict they delivered is to be taken seriously. The recognition was a long time coming. Bell published his theorem in 1964. Clauser ran the first experimental test in 1972. Aspect ran the experiments that closed the locality loophole in the early 1980s. Zeilinger pushed the program in directions that connected it to quantum information processing through the 1990s and 2000s. The loophole-free experiments came in 2015, almost half a century after Bell's original paper. The Nobel came 7 years after that. The slow pace of recognition reflected the discomfort the broader physics community had with the Foundation's question. For much of the late 20th century, working on the interpretation of quantum mechanics was not considered a serious career path. The standard advice to graduate students was to shut up and calculate. The Foundation's questions were treated as philosophy, not physics. The 2022 prize was, in part, a formal abandonment of that attitude. By awarding the highest honor in physics for Foundation's work, the committee signaled that the field had matured. The questions about what quantum mechanics says about reality were no longer considered idle. The experiments that addressed them were no longer considered fringe. The verdict was no longer in doubt. This shift matters for our story because it sets the stage for what comes next. The current generation of Foundation's experiments, including the Wigner's friend tests and the local friendliness violations on quantum computers, builds directly on the work the 2022 prize recognized. The new experiments are not separate from the older program. They are its continuation, asking sharper questions of the same hardware. The next decade of Foundation's experiments will likely produce results that the community will eventually have to interpret. Some of those results will narrow the interpretations of quantum mechanics that remain viable. Some may force the community to take observer-dependent reality more seriously than it has been willing to do. The Nobel Committee, sooner or later, will face the question of how to recognize this work too. The judgment may take another half-century. It may take less. What is clear is that the Foundation's program is no longer a sideshow. It is the most active and promising frontier in the foundations of physics, and quantum computers are the laboratories where that frontier is being explored. The current state of the Foundation's experiments is a small set of results obtained on small quantum systems. The Wigner's friend tests use a few photons. The local friendliness experiments on superconducting hardware use a few dozen qubits. The branch factors achieved so far are modest by any standard. The next decade is about scaling. The hardware is improving. The number of available qubits is rising. The coherence times are getting longer. The control over individual qubits is getting finer. Each of these improvements directly translates to the ability to run Foundation's experiments with larger friends, more complex agents, and stronger conclusions. The goal of the program, stated openly by the researchers leading it, is to push the friend up to a level where calling it not an observer requires special pleading. The exact threshold is not known. It depends on what you think makes something an observer in the first place. Some researchers focus on memory capacity. Others focus on the ability to perform internal reasoning. Others focus on the sheer number of degrees of freedom that an experimenter can, in principle, distinguish. By any of these measures, the friend in current experiments falls short of what most people would call a real observer. The branch factors are small. The internal complexity is limited. The agents do not reason in any rich sense, but the trajectory is clear. Hardware that can support a friend with thousands of qubits is plausibly within reach in the next decade. Hardware that can support a friend with millions of qubits is plausibly within reach in the decade after that. Whether such systems would count as observers in any deep sense is contested. But the contestability of the question is itself the point. The current experiments are easy to dismiss because the friend is obviously too small to count. The future experiments will not be so easy to dismiss. There is a deeper question lurking here. At what point does a quantum system count as an observer? The Foundation's program treats this as an empirical question. Run the experiments at increasing branch factors. See where, if anywhere, the violations stop working. If they keep working all the way up, the assumption that there is a special class of systems called observers, distinct from ordinary quantum systems, becomes harder to defend. The blur between observers and observed systems becomes a continuous one. If, on the other hand, the violations stop at some specific scale, that would be a major discovery. It would mean that quantum mechanics has a genuine boundary, beyond which the rules change. No such boundary has been found, but the search for one is now part of the program. This is also where the Foundation's program connects to questions about consciousness and the brain. Some theorists, most prominently Roger Penrose, have argued that consciousness involves quantum processes that are not yet understood. Most physicists do not accept this view, but the Foundation's program is, indirectly, providing tools that could test it. If consciousness involves quantum coherence at the scale of large brain regions, the same techniques being developed to test local friendliness with larger friends could, in principle, be applied to study quantum effects in living systems. This is speculative. The connection between consciousness and quantum mechanics is not established. Most working neuroscientists treat the brain as a classical system, at the scales relevant to perception and cognition. But the Foundation's program is creating the tools that would let the question be asked seriously, if it ever needs to be. For now, the program is more modest. It is about pushing the friend bigger, by increments, on better hardware, with cleaner experiments. Each step makes the conclusions harder to escape. Each step narrows the interpretations of quantum mechanics that remain viable. The endpoint, if the program succeeds, is a clear empirical statement about which classical assumptions about reality must be given up, and how completely. The endpoint will not be comfortable. It will be honest. The verdict of the Foundations program, as it currently stands, is sobering but not paralyzing. The classical picture of reality, in which the world has definite properties whether anyone looks or not, in which distant events do not influence each other instantly, in which experimenters freely choose their measurements, and in which every measurement produces one shared fact, is no longer tenable as a complete picture of the physical world. That is the bare statement. Now, consider what it means for everyday life. For everyday life, almost nothing changes. The world you wake up to tomorrow will look the same. The cup will still be on the counter when you reach for it. The chair will still hold your weight. The sky will still be there when you look up. Decoherence keeps the practical world classical. The objects you interact with are constantly being measured by their environment in the technical sense, and they behave as if they have definite properties at all times. The quantum strangeness is real, but it is not visible at human scales without special equipment. You will not catch yourself in a superposition. You will not have an experience that contradicts another observer's experience in a way that cannot be reconciled. Your brain, as far as we know, operates classically at the scales relevant to your experience. What does change is the picture you carry of what the world fundamentally is. The world, at its foundations, is not the world your intuition suggests. Particles do not have all the properties you would attribute to them before they are measured. Distant events are correlated in ways that respect the speed of light for signaling, but not for the underlying connections. Observers playing the role of friends in carefully isolated quantum experiments can, in principle, end up in states whose descriptions cannot be combined into a single shared account. These are real features of the physical world. They have been demonstrated experimentally. They are not metaphors or analogies or interpretive flourishes. They are what the data says, when the experiments are clean enough to leave no room for the comfortable alternatives. This changes how to think about what it means to be a part of the universe. You are, at the most basic level, made of quantum systems. Your brain runs on chemistry that runs on quantum mechanics. The reason your experience feels classical is that the systems you are made of are constantly interacting with each other and with the environment in ways that suppress the quantum strangeness through decoherence. The strangeness is real, but it is hidden under the classical surface that decoherence creates. What does this mean for questions like consciousness, free will, identity? The honest answer is, nobody knows. The Foundations program does not directly address these questions. It addresses what kind of physical world consciousness, free will, and identity are situated in. It tells us that the world is stranger than the classical picture suggested. It does not tell us how that strangeness reaches up to the level of experience. What it does suggest is that some of the assumptions you carry about the relationship between yourself and the world may need updating. The idea that there is a single, definite, observer-independent world that your senses imperfectly perceive is not the picture quantum mechanics paints. The picture quantum mechanics paints is more layered, more participatory, more dependent on the act of measurement than classical intuition allows. You are not a passive observer of a fixed external world. You are a quantum system embedded in a larger quantum system, and the boundary between observer and observed is, at the foundations, not as sharp as you might have assumed. This is not a license for any particular spiritual or philosophical reading. The data does not justify mysticism. It does not justify solipsism. It justifies a careful humility about how much of your sense of the world is built on assumptions that the experiments have shown to be limited. Live in the world as you find it. Drink the coffee. Hold the cup. The decoherent shell of daily life is robust. But know, when you look up at the sky, that what you are looking at is not quite the world Newton described. Not quite the world Einstein wanted. Not quite the world your everyday intuition assumes. It is something else. Stranger. More participatory. Still being mapped. We started this story with a chip the size of a fingernail in a quiet lab. We end it with the same chip, but with a different sense of what it has been doing. The chip has been measuring over and over in different setups, on different platforms, in different countries, that the comfortable classical picture of reality cannot survive contact with carefully designed quantum experiments. It has confirmed what the photon experiments confirmed. It has confirmed what the diamond experiments confirmed. It has confirmed what the neutral atom experiments confirmed. The verdict is consistent across every platform on which it has been tested. The interpretations of quantum mechanics that remain viable each pay a different price. Bohmian mechanics pays with locality. Copenhagen pays with realism. Superdeterminism pays with free choice. Many worlds pays with single outcomes. Relational quantum mechanics pays with absoluteness of observed events. There are no cheap interpretations left. There may never have been any. The cheap ones, the ones that asked nothing of common sense, were ruled out by the data decades ago. The deeper signal in all of this is what unites the surviving interpretations, despite their disagreements about which specific assumption to give up. They all agree that some cherished classical assumption must die. This is the actual content of the Modern Foundations program, not a single horrifying revelation, not a clean overturning of physics. A slow, methodical narrowing of the space of possible pictures of the world, until the only pictures that remain require giving up something that classical intuition holds dear. Pick your loss. Local realism, with its definite particles and finite speed influences, is gone. Either particles do not have definite properties, or distant events are connected in ways that ignore signaling limits, or experimenters do not freely choose, or measurements do not produce single shared facts. You can pick which one to release. You cannot keep them all. The program is not finished. The next decade of experiments will narrow the field further. Larger friends, longer coherence times, cleaner isolation, sharper inequalities. Each step will make some of the surviving interpretations more strained and others more attractive. Some interpretations may eventually be ruled out by data, just as local realism was. The Foundations community is working on exactly this. What is striking is that the program has moved, in the space of a single human lifetime, from being treated as fringe philosophy to being recognized with a Nobel Prize and run on commercial quantum hardware. Bell was an outsider when he wrote his paper in 1964. Today, the experiments his theorem inspired are central to the field, and the conclusions they reach are accepted, with caveats, across the working physics community. This is what scientific progress looks like when it engages with deep questions. Slow, careful, resistant to drama, driven by data. The verdict comes out, the comfortable assumptions fall. The new picture is uncomfortable, but more honest. The community absorbs the new picture eventually, and moves on to ask the next question. The next question, in this case, is enormous. If the classical picture of reality is wrong, what is the right picture? We have several candidates. We do not yet have a winner. The choice between them may take another century to resolve, or it may resolve in the next decade as quantum hardware matures. The pace of the answer is not in our hands. What is in our hands is how we think about the world while we wait. The honest position is the one the data supports. The world is stranger than your intuitions tell you. It is structured at the foundations in ways that classical thinking cannot accommodate. The interpretations of quantum mechanics that remain viable each ask you to give up something cherished. There is no escape from this. There is only the choice of which loss to accept. Whatever you give up something serious. Whatever you keep with the knowledge that you keep it because of preference, not because the data spared you the choice. The chip in the cold lab keeps running. The verdict keeps coming back. And the world we thought we lived in keeps shrinking, one experiment at a time, into a smaller and stranger version of itself,